This is not your dad's math. I'm Mike, and we are engineering an LED test circuit. In this part, we are prototyping the design on a breadboard. In the last part, we designed the circuit in KiCad. Today, we'll make sure that it actually works. We'll start by placing the LM358 dual op-amp on the breadboard. The end with the notch will be on the left side of the screen. Pin 1 is located in the bottom left corner, and we count the pins counterclockwise going up from there. This means pin 8 is in the top left corner. Next, we'll connect the op-amp to the power rails. Pin 4 is connected to ground. Pin 8 is connected to the 9-volt rail. Later on, we'll add an electrolytic capacitor across this power rail. But for now, we'll set it aside to keep it out of the way. Next, we'll create a 1-volt reference for the first stage op-amp. We'll use a 7.5K resistor connected to the positive rail and a 1K resistor connected to ground to divide the voltage. The middle of the voltage divider is connected to pin 3, the non-inverting input. We'll connect pins 1 and 2 together to buffer the 1-volt reference. Pin 2 is the inverting input and pin 1 is the output. Now, we'll use a jumper to provide the 1-volt reference on another row. The high side of a potentiometer will be connected to the 1-volt reference. I want to place it so that the wiper is connected to ground when the knob is turned all the way down, and 1 volt when it's turned all the way up. We'll set the potentiometer aside for now. We'll need another jumper to connect its other side to ground, and another jumper to connect the wiper to pin 5, the non-inverting input of the second stage. You can use the potentiometer to check that your jumpers are connected to the correct rows. It took me a couple tries to get it right. Next up, we'll connect a 47 ohm resistor from the inverting input on pin 6 to ground. This is the resistor that sets the current source's actual current using Ohm's law. When the potentiometer is turned all the way up, we'll be dividing 1 volt by 47 ohms to get approximately 20 milliamps. Next, we'll connect our NPN transistor, the 2N2222. The emitter pin will feed the current going into that resistor. The base will be controlled by the op-amp's output on pin 7. These two connections complete the feedback loop, which lets the op-amp do its magic thing. Finally, the collector pin will be connected 1 row above the op-amp. Now we need to use a jumper to connect another row to the positive supply. Our test LED will connect from the positive supply to the transistor's collector. Make sure that the LED's anode, the longer pin, is connected to the positive supply. We don't really need it for testing, but we'll add a 1 microfarad electrolytic capacitor across the power rails. Be sure to connect the longer pin to the positive supply. All of our wiring is complete, so let's add the potentiometer to the circuit. It takes a little bit of force to get the pins seated well. We still need some jumpers to connect the power rails on the opposite sides of the board. Now we can connect a 9-volt battery and test the circuit. When I turn the potentiometer up, we increase the current through the LED. In the design video, we started out by driving the LED directly in the op-amp's feedback loop. Let's try out that simplification to make sure it works. After removing the transistor, we'll connect the LED between the output and the inverting input. This means the long leg to pin 7 and the short leg to pin 6. After reconnecting the battery, we can see that this configuration works too. However, this really pushes the op-amp near its limit. The transistor we're using is rated to source 20 to 30 times more current. So let's swap the transistor back in for one more try. In the next video, we'll take our first step to creating a custom PCB for this circuit. We'll use KiCad to select footprints for all of these components, and we'll make our own footprint for the potentiometer. This has been Not Your Dad's Math. Thanks for watching.